Okay, now let's talk about something a little bit more physical, a little bit more mechanical. Okay. All right. So we said that the rotation group, rotation matrices, a rotation matrix can be described using 3 independent coordinates. Okay. So far, all our rotations have been matrices, which have 9 numbers. So that's too many. So let's look at that question, how to come up with 3 coordinates. Okay, so a rotation matrix can be parametrized using 3 coordinates. Okay, so here's one way. Okay, so this is not going to be abstract. In fact, what we're going to do is we're going to do reverse engineering. Okay, so we're going to look at a robot wrist. Okay, because robot wrists usually have 3 joints. So let's reverse engineer the robot wrist and figure out the relationship between the joints and the orientation. Okay? All right, so the wrist I'm going to draw. First, you might think there's no robot wrist that looks like that. But in fact, if you think about it, it's not that different. Okay, so here's the wrist. Okay, it's going to test my drawing skills. All right. Okay, so this. Okay, so not exactly a Renaissance perspective drawing, but you get the idea. Okay, so here's the way it works. So this is connected to the ceiling, okay, rigidly. And so I told you this is the wrist. So you say, well, where's the hand? Here's the hand, or here's the gripper. Okay? All right, so we rotate this link about this axis. Let's call this angle, let's use a different color. Call this angle alpha. Okay? Next, we rotate this wrist, or this joint, by angle beta. Okay? Okay? So if I rotate beta, what happens is this link, okay, rotates around this axis. This link moves. If I rotate alpha, this link moves. Okay? Okay, and finally, let me call this angle gamma. Okay? All right, so I have alpha, beta, gamma. And now let me draw a frame attached to the hand, like so. Okay, and I also have a fixed reference frame. Let's attach it over here. I don't want to clutter the drawing too much, so let me draw it this way. Okay, so this is the fixed frame. Okay, so the fixed frame origin is attached to this point. Okay, and this is the hand frame or the gripper frame or the end effector frame. Okay? All right, so obviously if I rotate alpha, what happens? This whole thing rotates, right? This whole thing rotates. If I rotate beta, this link rotates. Okay, so this link rotates up and down. If I rotate gamma, this last link rotates. Okay, see how that works? Okay, the important thing is that these joints all intersect at this point. Okay, they all intersect at this common point. So if I rotate these axes, okay, this orientation will change, obviously, right? But the origin of this frame always stays the same. Okay, so that's why I call this a wrist. Okay, because this frame orientation will change, but the origin will always remain fixed here. Okay, so you can see that. Okay, so in a typical wrist, robot wrist, alpha, beta, and gamma are controlled by motors. Okay, so we give input commands, and then these wrists rotate, and this frame changes orientation. Okay, so that's how it works. So what we want is we want the relationship between alpha, beta, gamma, and this orientation. Okay, so that's what we want. And so we're going to reverse engineer that. Okay, all right. So to do that, we're going to use our results from before. Okay, so let's label these frames. So let me call this frame 0. That's the fixed frame. And now I'm going to attach a frame to this link here. I'm going to call it frame 1. Okay. Another frame attached this time to this link. Frame 2. Okay. And let's say this frame is frame 3. Okay. All right. And we'll say XYZ is assigned in the usual way. Okay, so what I want is I want R03. Okay, and R03 depends on alpha, beta, and gamma. Okay, so now let's use property number, maybe it was 4, I think. Okay, and let's break this up. Okay, so this is R01 times R12 times R23. Okay, so we established that's true. Right? Now, what's R01? R01 depends only on alpha. Okay, I can rotate beta, I can rotate gamma. It does nothing to frame 1. Okay, so this depends only on alpha. Let's look at R12. R12, so frame 2 as seen from frame 1. So you're an observer. We've shrunk you down. You're standing at frame 1. Okay, you're observing frame 2, writing the orientation. You'll see that it depends only on beta. Okay, doesn't depend on alpha, doesn't depend on gamma, only beta. So it's that. And then finally, R23 depends only on gamma. Okay. Okay, so now it's a little bit easier, okay, to find these individual matrices. Okay, so now let's get to work through that. So R01, what's R01? So you're standing at frame 0, looking at frame 1, writing down the orientation. So if alpha is 0, okay, it's going to be the identity. Okay, as we rotate alpha, what does this frame do? Okay, it does this, right? as alpha rotates positively, this frame rotates about the z-axis positively. Okay, so the z-axis is always the same. Okay, so the z-axis always points in the same direction. What happens to the x-axis? It rotates in a plane. Y-axis also rotates in the xy plane. Okay, so this is going to be cosine alpha minus sine alpha, cosine alpha, 0, 0, 1. Okay, so that's what R01 looks like. Okay, so this is a rotation around the z-axis. So we're going to use this notation. So rotation around the z-axis by angle alpha. So let's use that. Okay. Okay, now let's look at R12 and R23. Okay, so R12, let's see what happens. You're standing at frame 1, observing frame 2. If I rotate beta, so here's my frame. If I rotate beta, okay, it's going to be hard to do. Okay, hold on here. It's like this. If I rotate beta, it's going to do this, right? Something like that. Okay, I think it's probably better to imagine it, okay? So if I rotate beta, the y frame always points in the same direction, okay? But the x frame and the z frame rotate in the xz plane. Okay, so what this is going to look like is the y vector always points in the same direction. Okay, but the x and z vectors change according to beta. Okay, so cosine beta minus sine beta, cosine beta. Okay, so it looks like that. Okay, so this is a rotation about the y-axis. So let's use the following notation. Rotation around y by beta. Okay, finally R23. Okay, you can probably imagine what this is going to be. It's going to be rotation around the x-axis. Okay, so it looks like that. Call this rotation around the x-axis by angle gamma. Okay, all right, so there we have it. So if I want the rotation of the end effector frame in terms of alpha, beta, gamma, all I have to do is multiply R01 times R12 times R23. Okay? Okay, so therefore, R03 is, all right, so I'm not going to ask you to do it in your head. I'm going to cheat. Okay, let's write it down. And I have to tell you, it's not pretty. And I hope never to have to write this down again during this course, but we'll do it this once. Okay, that's the first column. Cosine alpha, sine beta, sine gamma, minus sine alpha, cosine gamma. Okay, so I'm just, cosines are written C, sines are written S. Sine alpha, sine beta, sine gamma, plus cosine alpha, cosine gamma, and then cosine beta, sine gamma. Okay, one more column. Last column, cosine alpha, sine beta, cosine gamma, plus sine alpha, sine gamma. Sine alpha, sine beta, cosine gamma, minus cosine alpha, sine gamma, and then cosine beta, cosine gamma. Okay, finally, there we are. Okay, so there it is. You know, doesn't take great intellect to be able to multiply 3 rotation matrices. Reason we had to do it is because we now want to ask the following question. Okay, so here's the question. Question. Given some arbitrary, okay, so given some arbitrary rotation matrix R, okay, does there exist some angles alpha, beta, gamma, okay, that allows for the wrist to reach this orientation? Okay, so does there exist alpha, beta, gamma, okay, such that R equals this? Okay. So in a sense, we're asking, can this wrist reach any orientation? Okay. Can it reach? Perhaps there are some orientations that the wrist cannot reach. Okay. So if there does exist alpha, beta, gamma for every R, then that means this wrist is a universal wrist. It can reach any orientation, which is a good thing. Okay. Okay, so how do we answer this question? Well, in the absence of, you know, any clever ideas, what you do is you do the brute force method. Okay. So what's the brute force method? Okay. You set this matrix equal to R, okay, and then start looking at each of the terms independently. Okay. All right. Not the most elegant, but it works. Okay. So first thing you notice is that you can write tangent of beta, okay, as sine beta over cosine beta, naturally. Okay. So this means that beta is the inverse tangent or the arctangent of sine beta over cosine beta. Okay. But now, if you look at sine beta and cosine beta, you see that, let's see what we got here. Well, there's a sine beta. Okay, and cosine beta appears several places, here, 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 here. Okay, so one way to write this is as the inverse tangent of minus R31 over plus minus R11 squared plus R21 squared. Okay. So let's find beta this way. Okay, so R31 refers to the 3-1 entry of the rotation R. Okay, so find beta first is to find alpha as the inverse tangent of R21 over R11. Okay, and then third step, gamma is arctangent of R32 over R33. Okay? Okay, so that's the brute force method. Just look at this matrix very carefully, okay, and use your knowledge about trigonometry to find alpha, beta, gamma. Okay, one thing to sort of note, point of caution, is that if beta happens to be 90 degrees, okay, or minus 90 degrees, then what happens is that the wrist looks like this. Let me draw a mini version of the figure. Okay, so, all right. This part, this is the hard part here. Okay, this is really bad. All right, you get the idea, right? Okay. Okay, looks like some kind of an Escher drawing, but okay. So it's down here, okay, and the wrist is pointing up like that. Okay, so we had x, y, z, rotate about the y-axis, so now we have the axis oriented that way. So what was originally the z-axis is now over here. Y is still here. X is down here. Okay. Okay. Now in this case, now if alpha and gamma have to be some angles, then what happens is this frame is now rotating around this axis. Okay. Rotate alpha causes this frame to rotate this way. If I rotate gamma, it causes the rotation in the opposite direction. Okay, so alpha and gamma are rotations about the same axis. Okay, so that means there's many solutions. There's many solutions to this. Okay, so if alpha and beta is 90 degrees, beta is a solution. Okay, then alpha bar, 90 degrees, beta bar, is also a solution. Okay, provided that the difference in the angles, okay, provided alpha minus, sorry, there should be gamma here. Gamma and gamma bar. So alpha minus gamma and alpha bar minus gamma bar are the same. The difference is the same. Okay? Okay, so we now have a way of representing any rotation using three parameters, alpha, beta, gamma. Okay, so these alpha, beta, gamma, as described just now, are called the ZYX Euler angles. ZYX Euler angles. Okay, so there's our first three-coordinate representation for rotations. Okay, all right. Now, suppose I took the same wrist. Okay, let me try it. All right, I'm going to try to do a better job this time. Why is it? This is just killer. Okay, for the life of me, I just can't seem to draw this correctly. Okay, so suppose it's the same wrist. Okay, it's the same wrist. But now I define this to be the 0 position or the home position. Okay, same wrist, but now let's rotate beta by 90 degrees and say this is my wrist. Okay, so this is my wrist. Now I repeat as before. So I attach frames here, frame here, frame here. Okay, my fixed frame is here. Okay, call this alpha, beta, okay, gamma. Okay, I repeat the same analysis. Repeat the same analysis. Okay, so this is the same wrist. But it's a different, different 0 position. Okay, I can do that. I define this to be the position where all the angles are 0. Okay, now I can do the same analysis. Okay, I can say R is rotation about the z-axis by alpha, followed by rotation about the y-axis by beta, followed by, now here's where it changes. This is now rotation about the z-axis, z-axis by gamma. Okay? So it's the same wrist, so we know that this wrist can reach any orientation. Okay, but the formulas now change a little bit. Okay, so if I define alpha, beta, gamma in this way, okay, these are called the ZYZ Euler angles. Okay, so we can have many different versions of Euler angles, ZYX, ZYZ, or whatever orientation you prefer. You can call that to be X, Y, Z, whatever. Okay. Okay, let's stop here. And let's take our quiz now.